The force that has been silently pushing the entire universe apart for nearly 14 billion years may be losing its strength, and two of the most powerful telescopes ever built have now pointed at the same evidence from completely different angles, and neither of them can explain what they are finding. This is the story of dark energy, the invisible something that makes up roughly 70% of everything in existence, and why the combined data now coming in from the James Webb Space Telescope and the newly operational Vera C. Rubin Observatory has left cosmologists staring at a picture of the universe that no longer quite fits the theory they have spent decades building. The phrase terrifying is not hyperbole in this context at all. Dark energy is not a phenomenon in some distant corner of space that astronomers can study at a safe remove. It is the dominant ingredient of the cosmos itself, the force that determines whether the universe expands forever, slows to a halt, or eventually reverses. If it is changing, then everything physicists thought they understood about the long-term fate of the universe may need to be reconsidered from the ground up. To understand why this matters, it helps to know what dark energy actually is, or rather what scientists still do not know about it. When astronomers discovered in 1998 that the expansion of the universe was accelerating rather than slowing down as gravity would predict, they had no good explanation for the force driving that acceleration. They named it dark energy and built it into the standard model of cosmology under the simplest possible mathematical description. A cosmological constant, an unchanging uniform pressure woven into the fabric of space itself that pushes outward with the same strength at every point in the universe for all of time. This simple, constant version of dark energy is called lambda, and for over 2 decades, it successfully predicted enough observations to remain the accepted foundation of modern cosmology. But it also came with a nagging problem. Nobody could explain where it came from, and the value predicted by quantum physics for the energy density of empty space differed from the observed value by a factor of roughly 10 to the power of 120, one of the largest discrepancies between theory and observation in all of science. Most physicists assumed this mismatch reflected some unknown cancellation mechanism they had not yet discovered, rather than a fundamental problem with the model itself. The new data from DESI, Webb, and now Rubin has given those physicists considerably less comfort than they had before, and the scientific pressure to find a better explanation has never been more acute than it is today. That uncomfortable background tension has been simmering in the field for years, and the latest data from multiple instruments has started to make it considerably worse. The first major warning arrived in March 2025, when the Dark Energy Spectroscopic Instrument, known as DESI, released the results of its first 3 full years of observations, covering measurements of nearly 15 million galaxies and quasars spanning 11 billion years of cosmic history. This was more than double the number of objects surveyed in DESI's previous data release, and the improved dataset carried more statistical weight than anything the collaboration had produced before. The findings, published in multiple peer-reviewed papers and presented at the American Physical Society's Global Physics Summit in Anaheim, pointed towards something unsettling. When DESI's data was combined with earlier measurements of the cosmic microwave background, distant supernovae, and weak gravitational lensing, the combined dataset showed mounting signs that dark energy's influence on the universe's expansion rate was not holding constant. Instead, it appeared to be weakening as the universe aged, growing stronger early in cosmic history and fading gradually toward the present. Researchers described the finding at the time as another mind-blowing change to our understanding of the universe's behavior, and the phrase was not hyperbole. The cosmological constant is literally the most fundamental assumption built into the standard model of how the universe works, and the DESI data was suggesting it was wrong. The significance of this is difficult to overstate. The cosmological constant model of dark energy, lambda, explicitly predicts that this should not happen. Lambda is by definition unchanging. If dark energy has actually evolved over time, it is not a cosmological constant at all, and the standard model of cosmology, known as lambda CDM, would need to be fundamentally replaced rather than merely adjusted at its edges. Cosmologists reach for alternative theoretical frameworks, including a class of models where dark energy is not a fixed property of space, but a dynamic field that changes over time. Similar to the fields that drive inflation in the earliest moments of the Big Bang, these models go by names like quintessence and phantom energy, and they offer ways to fit the DESI data more naturally than the cosmological constant does, but they also introduce entirely new unknowns and require physical mechanisms that nobody yet knows how to identify or measure directly. Some physicists have pointed out that the DESI result, if confirmed, would represent one of the most important shifts in fundamental physics since the 1998 discovery of accelerating expansion itself, comparable in magnitude to discovering that gravity behaves differently from what Newton and Einstein described. The comparison is not made lightly, and it underscores just how seriously the scientific community is taking a signal that has not yet cleared the conventional threshold for a confirmed discovery. The DESI collaboration was careful to communicate appropriate uncertainty around the result. Taken in isolation, DESI's own data remained broadly consistent with the standard lambda CDM model. The hint of evolving dark energy only emerged clearly when the DESI measurements were combined with other datasets, meaning the signal depended on a combination of independent observations rather than any single decisive measurement. The statistical significance of the combined signal hovered around 3 to 4 sigma, a level that cosmologists treat as genuinely interesting but not yet conclusive, since the field conventionally requires 5 sigma confidence before announcing a confirmed discovery. What made the result impossible to ignore was not its statistical strength alone, but the fact that this was the second consecutive DESI data release to show the same pattern. The first data release in 2024 had produced a similar hint at lower statistical significance, and the 2025 release, with more than twice as many galaxies, had made the hint stronger, rather than dissolving it as a statistical fluke. If the signal continues to strengthen with each additional year of data, the implications will eventually become impossible to dismiss, because DESI's excellent performance led to an extension of its original mission. It will continue observations into 2028 and further expand its map of the universe, meaning the question of whether dark energy is truly evolving will continue to sharpen with each passing year before Rubin's data reaches a comparable level of precision. James Webb entered this conversation through a different door. Its observations of the earliest and most distant galaxies in the universe have repeatedly produced results that sit in tension with the same standard cosmological model that DESI's dark energy data is straining. The unexpectedly bright, unexpectedly massive galaxies Webb keeps finding in the first few hundred million years after the Big Bang require stars and galaxies to have assembled faster than the standard model predicts. And some researchers have specifically pointed to a possible connection between evolving dark energy and the early galaxy problem. A 2024 paper published in the Astrophysical Journal explored exactly this link, arguing that a dynamic dark energy field with higher energy density in the early universe could have accelerated early. Structure formation enough to explain the excess brightness Webb keeps observing at high redshifts. If that connection is real, then Webb's impossible early galaxies and DESI's weakening dark energy may not be two separate anomalies at all, but two different symptoms of the same underlying crack in the standard model, and the fact that two completely different telescopes using completely different techniques arrived at. Data pointing in the same direction has given that hypothesis considerably more credibility than it would have carried on the strength of either instrument's findings alone. The Vera C. Rubin Observatory officially joined this conversation in a significant way in 2026. After releasing its first images to the world in June 2025 and spending the following months commissioning its systems and refining its calibration, the observatory officially launched its primary scientific program, the Legacy Survey of Space and Time, in July 2026. Over the next decade, Rubin will scan the entire southern hemisphere's sky repeatedly, building an enormous data set of billions of objects that will provide an independent and potentially definitive measurement of dark energy's behavior over cosmic history. One of its primary scientific goals, built into the mission from the very beginning, is testing whether dark energy evolves over time, precisely the question DESI has made so urgent, and researchers specifically designed the mission's observational strategy with this test in mind rather than adding it as an afterthought to a telescope built for other purposes. Rubin will approach this question through several independent techniques, including the distortion of distant galaxy shapes by gravitational lensing, the statistics of galaxy clustering across vast cosmic scales, and one of the most comprehensive supernova surveys ever conducted, tracking how the brightness of exploding stars across a wide range of distances encodes the universe's expansion history over billions of years. Scientists working on Rubin have specifically noted that the telescope's weak lensing data alone, after a full year of sky coverage, is expected to reach a precision on dark energy's properties comparable to what DESI has achieved through its galaxy surveys, providing an independent check against an independent source of systematic errors. The significance of having two instruments of Rubin's and Webb's power simultaneously trained on the same fundamental question cannot be understated in the context of how these mysteries normally get resolved. Big questions in cosmology have historically required independent verification from multiple directions before the field accepts a new result as genuine. DESI's dark energy signal is intriguing precisely because it appeared consistently across two successive data releases, but it is still one instrument, relying primarily on one measurement technique. Rubin's gravitational lensing data, once it accumulates enough sky coverage, will produce a precision on dark energy's properties, roughly comparable to what DESI achieves through galaxy surveys, but using completely different physics and completely different sources of systematic uncertainty. a result that survives both types of measurement from two entirely independent observatories working in different wavelengths of light from completely different physical locations would be extraordinarily difficult to explain away as a calibration error or a subtle statistical artifact. And that combination of independent confirmation is precisely what the field needs before any claim this significant can be treated as settled science. Scientists involved with both telescopes have been direct about the stakes involved. If dark energy is truly weakening over time rather than staying constant, the universe's long-term fate changes in ways that depend on exactly how it weakens and over what timescale. The simplest constant dark energy model predicts a universe that expands forever into a cold, diffuse, isolated end state, sometimes called the Big Freeze, where galaxies drift apart, stars burn out, and nothing new can form. A weakening dark energy, if it continues to fade, could eventually slow the expansion below what gravity can overcome, potentially reversing the expansion and ending in a big crunch, a collapse back to a hot, dense state. Alternatively, if dark energy is a dynamic field that oscillates rather than fades monotonically, the fate could be far stranger still, with expansion accelerating and decelerating in cycles that could tear structures apart or compress them in sequences no current theory fully predicts. The difference between these possible fates is not something that would be visible on any human timescale, unfolding instead over hundreds of billions of years, but the significance of knowing which path the universe is on carries its own kind of weight, as a statement about the ultimate nature and destiny of all the matter, energy, and structure that has ever existed. None of these dramatic possibilities have been confirmed. The DESI signal is a hint, not a verdict, and many cosmologists remain carefully skeptical, pointing out that similar hints in past datasets have sometimes dissolved when better data arrived. What has shifted in the past year is the number of independent lines of evidence pointing in the same uncomfortable direction. Rubin's first full year of LSST data, expected to be published in late 2027, will represent the most powerful independent test of the evolving dark energy hypothesis yet attempted, and the scientific community is already watching closely. Whatever Rubin finds when it finishes that first full year of mapping the southern sky will either confirm that the standard model is genuinely breaking down, or show that the hints from DESI and Webb were something the next generation of instruments was able to explain away. Either outcome would represent one of the most consequential results in the history of cosmology.